kind of divide up my time into two pieces. First, I will essentially finish the tutorial on the Flash, outlining a couple of special features which you might not know they exist there and might be interested in using it even for your research. And then in the second part, I will kind of slide in a brief science talk and building up on the arguments essentially Chris was discussing and even Eve was discussing a couple of days ago on the formation of disks, protostellar disks in a turbulent environment. So yeah, let's get started with flipping through a couple of what I would call special features. And so far, this is a little bit the features we were talking about on the Flash code. So apart from the solving, of course, the hydrodynamics and magnetohydrodynamics, it comes with gravity solvers, which we talked about, different kinds. In particular, for star formation, it's of course very important to include gravity into your simulations, otherwise you won't get any stars. And if you might get stars, you don't want to do your calculation any further because you essentially had to increase your resolution and also had to increase more physics, down to maybe a nuclear network. So you can replace your protostars with sync particles. We discussed about this, how this works. And if you are interested in radiation, and this is of course also a very important part of the physics, talking about star formation is radiation. So there are at least two approaches which you might build up your further research if you use the Flash code. One is the multi-group diffusion module. The other one is based on a ray trace algorithm, so far coupled to ionization radiation. So this is essentially the summary of the last 4 days here. And just to essentially address this point, that of course the Flash code is what is called a multi-species code. You can essentially initialize and also keep track of different species in your simulation. And here are the list of essentially the properties which you can assign to every species. So you can assign some atomic properties. Most of the time you don't really need them, but of course for a nuclear network you might need them. And you can assign internal properties like the binding energy of your species, of your atom or molecule you're putting in there. And this is all these, or this particular feature is of course interesting, particularly interesting if you do, for instance, a chemical network. So if you really want to, for instance, calculate the formation of molecular clouds, you need a time-dependent chemical network to really decide where your H2, your molecular hydrogen resides. So, and you can build your chemical network essentially on this database, on these multi-species properties. So this is something you don't really need to take care of, which is, if you look about how to build a large computer simulation, this is always takes a lot of time to build up all the framework around it, and this is essentially already there, the framework to keep track of the properties of many different species. Just to show you a piece of code, how to initialize, for instance, your properties, or initialize, in this case, for two different species. You just call this function here, multi-species set property. You have to assign a name to it, and then go through the list of properties, which I outlined here, and set the particular properties specific to this one single particle type. So that's very straightforward. All the interfaces are already there, and this function essentially puts it into the memory database. So this is one thing I wanted to show. Coming essentially also with the material properties, and usually I put in here the directories where you find all the specific modules here. Coming with the material properties are things like viscosity and magnetic resistivity. Of course, for instance, if you want to do a controlled turbulent simulation, for instance, where you really want to probe the dependence of your result on the physical viscosity, the physical kinetic viscosity, this can be easily implemented in your code. So far there are two types. Always a constant viscosity, of course, and then what is called a Spitzer thermal viscosity, so a viscosity which scales with 5/2 of the temperature. So that's also fairly straightforward, and very similar for the magnetic resistivity. If you really want to probe, your dependence on, for instance, ohmic diffusion, there is also already at least an interface to it. So far, it handles only constant magnetic resistivity. So you essentially diffuse out your magnetic flux here if you switch on this constant, or switch on this module. There's also thermal conductivity, so the transfer of heat. And this might be important if you do, for instance, galaxy-type simulations where you need heat conduction to get, for instance, things like cooling flows right. And there's also an interface already to it. So you just have to essentially include the physics of your particular heat conductivity, but all the interfaces is there already. So far, there's again a constant heat conductivity, and again something which is named after Spitzer. And here you see a fairly complicated formula which comes with this conductivity. So this is already implemented there, but you can imagine this is fairly easy to extend to your own physical model you want to put in here. There's another interesting module. So the Flash is, at least to a certain extent, capable to handle relativistic MHD, or I shouldn't say MHD, relativistic hydrodynamics. MHD is not yet included here. And this is, of course, interesting for you if you deal with anything, with high velocity flows which are close to the speed of light. For instance, HEN jets which can acquire Lorentz factors much greater than 10. So to get the physics right there, of course, you need to really include, have to compute this in a special relativistic framework, which is already provided here in the Flash code. And this goes back to a work of Andrea Mignone. He got a little bit frustrated actually with the Flash code. So he wrote his own code because he had some issues to initially implement the relativistic hydrodynamics in the Flash. So he has his own code now, is the Pluto code. So I guess a lot of features you find here in the Flash code you also find in the Pluto code. And if you essentially you can kind of compare, or at least these approaches are very comparable. So what it does here, it solves this equation, and the important thing is, of course, the Lorentz factor. Everything scales with a certain power of the Lorentz factor, which you have to take into account here. And the units you use here are the typical units you use in special relativistic research. So you set your speed of light to 1, and your velocities are essentially in ratios of the speed of light. There are only a few examples. which you find in the simulation main directory here. There's, for instance, a SOT, special relativistic SOT experiment. So an explosion, this is in 1D so far, but it also works in 3D, and a Riemann type problem, so with density discontinuities at the beginning. And here, just to show you some results here from these simple setups. And notice here, this is already with a speed of light, so the velocities acquire about 99% of the speed of light. So this is quite dramatic. And the code doesn't crash at this point. Yeah, and as I said earlier, so so far there's no connection to magnetic fields, so there's no relativistic MHD yet. And I was actually talking lately to Andrea Mignone, and he will implement this, at least for the Pluto code. And I guess if this is ready, one can also rip this out and put it back to the Flash code if you want to continue, for instance, working with the Flash code with special relativistic magneto-hydrodynamics. And essentially building on this, there's also a cosmology module. Might be a little bit surprising because as far as I know, they are not, I don't think there are any papers actually out on this, on simulations done with the cosmological module with the Flash code. But in principle, you could also do full cosmological simulations. So far, I haven't done this. And the main idea is, and this is essentially true for every code, what you do is you rescale your variables in variables which are called co-moving variables. You essentially take out the dependence on the expansion of the universe, the scale factor. So for instance, the matter density, if the universe expands, dilutes as normal matter, so with the volume, so it gets an scale factor to the power of 3 here. And notice here, these are the co-moving variables, whereas the tilde variables are the physical variables at a given epoch. And you use these co-moving variables and essentially stick them into your hydro, or in this case even the MHD code, which is not shown here in the list of equations, but it actually should also work for magnetic fields. So because of this simple rescaling, and what you get here is you get a couple of terms proportional to the Hubble rate, and these are essentially treated as source terms in these calculations. So if you put them essentially on the right-hand side, of most of these equations, they appear as source terms, and this is how the entire framework handles the expanding factors essentially. So this is the technical magic behind using cosmology or doing cosmological simulations with the Flash code. So every time step, essentially the physical variables can be recomputed just by multiplying it with the right power of the scale factor. And of course, you also, on top of it, you want to get the background essentially. So we are talking about an homogeneous background which is expanding. So you have to solve the Friedmann equation to get essentially the scale factor for every epoch, for every time you're interested in. And this is done, essentially this is the differential equation you want to solve here in this case, done with a fourth order Runge-Kutta regime. And then of course the scale factor depends then on the composition of the universe, and this is you have the freedom here for in the current approach to essentially include matter This is essentially mainly dark matter in this case, can include radiation, cosmological constant, so far it's just a constant, and also the curvature of the universe. If you don't like a flat universe, can also, by essentially adjusting these numbers, you will get an open or an closed universe. And yeah, you just have to give, essentially, to solve this equation, the Hubble parameter today. Yeah, and here is essentially the list of runtime parameters. They are essentially self-explanatory. So you see, you give all these quantities in dimensionless. So you rescale, as outlined here, everything to the so-called critical, to the critical energy density, meaning critical means a flat universe. All these quantities are scaled to these critical values, and you just plug them in here, and then yeah, can essentially run your cosmological simulation. Maybe you want to adjust here a little bit your standard parameters, so the default parameters to the latest result of Planck. So I guess this increased a little bit compared. It should be of the order of 68 or so kilometers per second per megaparsec, and also the dark matter decreased a little bit to, I think, 0.8 or 0.28 or something. So that is seems to be fairly straightforward, and I guess it should, and one day at least, try it myself. I never did a cosmological simulation with the Flash code. And as I said, it should also, you also can include magnetic fields. So the magnetic fields will be rescaled essentially the same way than radiation does. So similar to this term here. So you rescale your magnetic field with a power of essentially a to the a squared, and then you get your physical value for the magnetic field magnitude. Yeah, as I said, so far this module is not heavily used, at least to my knowledge. Hence, we find only one example in our setup tree, in our simulation main tree. It is called the pancake setup, which goes back to an analytic solution of Seldovich to the 70s, of the last century. And this is essentially an ellipsoid, which essentially then collapses to a pancake. So the short axis collapses first, so the thing gets flatter and flatter. And this is done also in an expanding background. So this is something you can start off and just have a look how this works. And I guess this is the last module I want to bring to your attention. It's and this question was already raised, whether you can essentially also treat particles in a cell, meaning that you can, because there might be circumstances where essentially your continuous description, so talking about continuous densities, when you talk about your fluid motions, might break down. And this is, for instance, true for for situation where your gyro radius becomes much larger than the length scale you are considering. And this is, for instance, true for if you do research in the solar magnetosphere. So all these people, they're studying the solar magnetosphere, are using codes like this with particles rather than a continuous fluid. But at the end of the day, you don't want to treat every fluid, every particle as individual particle, because this might get very, very time consuming if you treat, for instance, ions and electrons as individual particles, because they also have their individual time step. And you can imagine electrons are quite fast. So you want to treat them as still as a continuous medium. And hence you do what is called a hybrid simulation. You combine your fluid, your MHD essentially, with a particle approach, so a pure where you just solve individual for each particle the Newton's equation. So this module also exists, and you are free to, of course, test it out. And how does it work? Of course, you have to accelerate. In this case, it is essentially, as you see here in the directory tree, so the force which these particles feel so far are the Lorentz force, so they're accelerated by magnetic fields, and hence you have to solve for your individual particle essentially, or all the particles you put in your simulation. These equations, essentially you apply the Lorentz force as an accelerating force to your particle here. And then in this case you have to essentially map back your particle properties onto the mesh, because the mesh particle or the mesh fluid also reacts on any change, of course, of your ions in your simulation. And this is done here with two functions essentially. So you map the particle properties, in this case the mass and the charge, onto the mesh, and you do also, or the mass, and in this case actually more the current essentially of the particle, and you do it also the other way around. So you need to accelerate the particles also the mesh information. You need to know the information for the magnetic fields and so on. You want to interpolate these quantities onto the position of the particle, and there's also an interface to do this, to do an interpolation of your continuous quantities onto the point where the particle resides at this particular times. So far there are two ways to do this. One is just a linear, the simplest way you can imagine, a linear interpolation, back and forth, and then Selling cloud algorithm, or you can extend this a little bit to a second order scheme, so a quadratic scheme. And you advance these particles essentially, so there are different options, as we were discussing already when we talked about the sync particles. So you can use a simple forward Euler approach, or a Runge-Kutta, or even the variable time step leapfrog, if you like, to advance these particles. Of course, there are certain restriction, as very similar to your CFL criterion for fluid motions on your grid. Due to the particles, you don't want to allow the particle to move further than a grid cell within a time step. So you assign an individual time step to your particle, and this is again very similar to the approach we did already for the sync particles. And again, this is very similar to a continuous fluid. You also have to look at the possible waves you might generate. And in this case, you might generate so-called plasma waves or Whistler waves, and you have to account essentially also the speed of Whistler waves, and also restrict essentially the Whistler wave not to propagate any further than a grid cell within a time step. So you assign a time step to this as well, and this is essentially scales with the time step scales with this number. You see that's fairly sensitive already to the grid spacing, and you have to be aware that your simulation might get, fairly slow if your particles become fast, or if you have fast plasma waves in your simulation. So this is just to aware you of the usual problem of any additional physics. Whenever you put in kind of new physics, most of the time, or for all of the time, I guess, you also can assign an individual time step to this physical problem, which you then also have to include in your simulation to make it not only stable, but also to get a physical solution out of it. Okay, I think this is about it. What I wanted to put your attention on the what I would call special features here for the Flash code, so things you might not know immediately. And okay, here again a list of the properties of your particles you can assign to, and this is of course the mass and charge in the first place. And then I just want to draw your attention to a few ongoing developments concerning the Flash code. And I guess you already had an entire week more or less about hearing about chemistry. And this is also something, there is already a piece of chemistry by, so a chemical network developed by Simon Glover, which is already available in the Flash code. There's also a publication out of it. But there's also an ongoing development putting a chemical network called Chrome to the Flash code, and this seems to work so far quite well. So this is essentially an separate solver for the chemical network, depending, of course, on your species you put in here and the complexity of your fluid you treat. Then there's an ongoing, essentially, development on the radiation transfer, and we were talking about this yesterday. So we are essentially probing whether we can also account for scattering if we kind of extend this ray tracing approach we were talking about to what is called parallel rays and sweep the entire grid with multiple angles of parallel rays to account for photon scattering. We are still testing this and hope that it might work out at least and might be applicable for certain research properties here, or certain research fields. In particular, we are looking for protostellar disks. So we hope we get this to work in a dynamic environment as well. And maybe I'm not entirely sure whether Paul last week was talking about this tree call approach. This is essentially something very similar to a tree-based gravity solver, and you use the same technique essentially to calculate the column density at every grid point in more or less one sweep in your simulation, assuming the radiation, or interesting for the radiation which comes essentially from outside of your simulation box. So this is, there's already some frameworks there to calculate the column density based on this tree call algorithm. Okay, that's about it. I wanted to say about the Flash code for this week. Are there questions? No questions? Yes?
With the plasma wave, why does it scale to the cell size square, whereas something like the Courant generally would be, in contrast to, say, like the Courant condition? Like, why is there a squared scale at the end?
that looks somehow reminiscent of a diffusion type process. So that, yeah, I can't, at this point I can't say much more why it should scale with dx squared, but it looks like very much like what you would expect for diffusion as well.
So I don't know the technology, but generally that sort of scaling is what you get when you get a second order differential operator. Like use an explicit scheme. The reason it scales as dx in first order for hydro is because all the differential operators are first order. They look like divergences and velocities and things like that. So I don't know if these equations have a double square anywhere, but if they do, that's why.
Yeah, I mean that the same is essentially true, yeah, for diffusion type process. I don't know if this time step is linked to a second order scheme, or I think it actually comes straight from analyzing essentially the plasma wave traveling here.
Why do you need to use a full order Ruki-Kuta for the expansion factor in cosmology?
Why you have to do a fourth order Runge-Kutta?
Because the bottom use leapfrog or something like that.
I mean, you essentially can do this with any other solver as well. I mean, this is not a very expensive one, and you can imagine that, you know, from one time step to the other, it doesn't change much anyway, so it should converge also very quickly. So.
Yes, but this iterator not conserve the fundamental quantities or yes.
You wouldn't use leapfrog for this because, I mean, you want to use leapfrog for something that where the equation is supposed to be energy conserving, where the system is symplectic, but this equation doesn't have that property. There's no advantage to using leapfrog for this form of equation.
So further questions to the Flash code? I mean, I'm still around. If there are questions in the afternoon, you know, you're welcome to see me. Okay, at the second half of this lecture, I actually want to shift topics a little bit and discuss essentially a problem which was already addressed by Chris. Nevertheless, I think it is worthwhile to build on this and see how we can essentially form disks or protostellar disks in a turbulent environment, because there are particular detailed studies by Daniel Seifried, a postdoc in Hamburg. And yeah, first observationally, and this is also already something Chris showed to you, is essentially this beautiful work by Tobin and co-workers discovering more or less a highly resolved, what is called a class 0 object, in which resides or which is surrounded by a protostellar disk. And it nicely kind of follows a Keplerian rotation, so this is a very convincing proof essentially that these very, very early type disks should already exist, and so the size of the disk here is of the order of I guess 200 AU or so. So that's a fairly big, here the scales, yeah. Here a fairly big protostellar disks, which some people would claim these things shouldn't exist because of this problem of magnetic braking.
What is the black ellipse on the corner of those diagrams? It doesn't look like, the disk is obviously in the center, but what's the black ellipse down in the corner?
Oh, I guess that's a beam size or so, yeah. And I think this graph you also already have seen. So the idea is here to essentially probe the influence of magnetic fields in certain density regions. And yes, you can see that most of the cores, so this region here, are essentially supercritical, meaning they have mass to flux ratios of the order of a few, not very dramatically, but if you do numerical simulations with a very idealized setup, these small numbers essentially tell you that you're not finding a disk in your simulations if you're not starting with at least something which resembles a little bit realistic initial conditions. So magnetic fields are there. Most of the cores are slightly supercritical. And here's again this idea of what does it mean, supercriticality. So it means that essentially the magnetic fields cannot hold up the collapse of a cloud core. And if you would increase the magnetic fields, you wouldn't allow the cloud core to collapse. It's essentially an argument kind of similar to a thermal pressure. You're holding up the collapse, so the magnetic fields are counteractive to the gravitational collapse. So, and if you do, for instance, simulations as pictured here a little bit, you start with a very smooth rotating cloud core threaded by a magnetic field. What you get typically are these objects, namely if you increase or decrease, so to say, your mass to flux ratio, you are losing your disk, which you might find in regimes where the mass to flux ratio is of the order of 5. You see a disk form, but if you decrease it a little bit, you're essentially losing your disk in your simulation. The magnetic braking is so strong, it takes away so much angular momentum from this core that you have essentially a spherical collapse. And this happens, so the taking away of the angular momentum essentially happens on fairly large scales already. It's not something which is important at the very center of this core, but it's important on essentially on the scales. You really want to form your disk on scales more than 100 AU or so. So essentially, if you want to lose, for instance, flux to get a disk at the end of the day, even if you start with a strong magnetic field, you want to make sure that the flux loss happens actually on fairly large scale already. So, and again, in this regime, or in this research topic, there are a lot of catastrophes, and this is called a magnetic braking catastrophe. So, because there's supposedly, if you do studies like this, you're not finding a disk, so you're essentially you're taking away too much angular momentum by magnetic braking. So, of course, there are a couple of possible solutions. As I told you, that one idea is, of course, to get rid of the magnetic field, so you lose your magnetic flux. You could do this in principle by ohmic dissipation or ambipolar diffusion, and the process which is termed turbulent reconnection. But again, I have to point this out that if you want to do this, this should happen on fairly large scales. And most of these processes, in particular ohmic resistivity, this is something which is only active in very high density regimes in very close to your protostar, essentially, not at these scales of 100 AU. So these are most of these flux loss issues here, or flux loss possibilities. They are active on high density regimes in the center of your disk. That might actually not be true for the turbulent reconnection. This is a process kind of similar to turbulence itself. So this can happen on all scales, essentially like a turbulent cascade, similar to a Kolmogorov type cascade of cascading kinetic energy. And here you have a similar picture where you have reconnection happening on all scales, essentially where turbulence is active. And of course, you could also include some Hall effect, which might be also able to reduce your magnetic flux here. Sorry, it doesn't reduce the magnetic flux, but it could, in principle, help you to kind of redirect your fluid and speed up, or create a disk. But this is, of course, depends on essentially the sign of the magnetic field. It can help you, or it also can prevent, of course, disk formation. And there's a study, for instance, by Lee and Krasnopolsky, trying out all these different effects. And with these idealized setups, they are not getting a disk. So essentially this study shows again that this potential flux loss by ohmic resistivity or ambipolar diffusion doesn't really help to form a disk, because it is only active at the high density regions. And they actually, 2 years ago, they still stated this is an unresolved, or this problem remains unresolved, which I would say it should be, it's more or less solved by now. At least we know how to form disks. This is essentially then done if you kind of include a little bit of turbulence in your simulation. So if you either perturb your cloud core, perturb the density in your cloud core, or put an initial velocity field. So what happens here is that you create structure there, and as we will see in a second, you in a situation like this, you actually get back your disk. And Daniel Seifri did a parameter study on, essentially turbulent cloud cores, and he always finds a disk in individually collapsing regions. And if you do a setup like this, it doesn't really mean that your collapsing object appears at the center of your cloud core. It can appear also further out, despite the fact if you even if you start with a density profile which is concentrated towards the center, just because turbulence creates also individually over densities which might then collapse. And I should point out that some of these simulations, they didn't start with rotation whatsoever. So most of these simulations done before, essentially they started with a rotating cloud core. So this entire cloud core initially was coherently rotating, but it turns out that to form a disk again, you don't really need this. You don't need to have your entire cloud core spinning to form individual disks around your protostar, even in this very early phase. Yeah, talking about the rotation of the cores, of course, there is old studies and ongoing studies to essentially quantifying the rotation of these cloud cores of the order of of the size of about 0.1 parsec, and these are the typical numbers from Alyssa Goodman, so more than 20 years ago, or about 20 years ago. And these numbers are typically a little bit less than if you compare it, for instance, to galactic shear, and the idea was maybe they are generated also by turbulence. Nevertheless, it's not really clear whether these numbers are would hold up, are real in this sense. There's a recent study by Sami Dib and Alyssa Goodman is also on this paper, essentially comparing synthesized, comparing simulation with using synthetic observations again to quantify the spin of the individual cores. And turns out that these numbers here are typically overestimated, way overestimated by a factor of by an order of magnitude typically. So and it turns actually out that this that the observations are, if you compare to these simulations, are essentially compatible with no rotation, no overall rotation at all. So these cores might not rotate whatsoever if they have a much lower angular momentum than quoted 20 years ago. Yeah, and this is essentially the outcome of one of those simulations here, including Turbulence. And what you see here, this is on a 200 AU scale. And you have seen similar pictures by Chris from the Myers study here. You essentially recover a disk, and this would be a situation, so this is a master flux ratio of the order of 2. This would be a situation if you compare it to a idealized initial conditions. If you don't put in any turbulence, you will not see a disk like this. So that I have a couple of animations. You can kind of see it is anything else but a simple build-up of a disk. This is a highly complex process due to the high accretion rates, essentially. So the entire core accretes quite a mass from the envelope. So the accretion rates are of the order of 10 to the minus 4 solar masses or so. And the accretion comes into clumps even. That means that the disk gets internal structure, gets spiral arms. So in this case, you even find it fragments. You find binaries, but both in this case also have an individual disk around them. So this is a highly kind of complex picture, and it's also not so easy to really quantify the different stages. So you also have the impression that the size of the disk might vary, at least if you just trace the density here. Yeah, and so these are essentially different cores in more or less the same simulation. So the individual collapsing objects are surrounded by a disk, and this is also, so the previous movie I've shown you goes back to a collapse of a massive cloud or a more massive cloud core of about 100 solar masses, whereas this is a cloud core of about 2 solar masses, so a low mass cloud core. And even in this situation where you have very little turbulence in this sense, so and in this case it's actually if you like, a worst case where you still start with a homogeneous density distribution, or a smooth density distribution I should say, and there's only subsonic turbulent motions put on top, but on the way of the collapse the turbulent motion create density structures which then individually collapse, and in these collapse, or in these class 0 objects, if you like, you see these disks here. Here said this is for a low mass core. You get a similar, maybe less dramatic accretion events on these early type disks. So this is a core of about 2 solar masses, and you very quickly get a disk here from starting off with, which looks like a filament. And of course, you also want to quantify the properties, whether we are not only seeing a flat density around the central object, or whether we can really talk about a Keplerian disk. And here's essentially an analysis of the disk itself. So you see the rotation velocity more or less follows nicely a Keplerian structure, Keplerian profile here. And of course, in this case, your radial motion, so the motion, the gas which is essentially then accreted by the protostar, should be subdominant, and this is indeed the case here. So the dominant component is the rotation, which essentially identifies as a disk, but this follows also quite closely a Keplerian profile. And then, of course, you can ask yourself, what is the actual mechanism? And to form the disk, is it flux loss or something else? So Daniel was looking actually at this quantity, the mass to flux ratio, and probed it over the evolution of the disk. And it turns out that, except for one case, essentially, it doesn't change much. It doesn't, and this is measured on the scale of the disk size, about 200 AU. So this is where we actually need the flux loss to build up a disk. And it turns out at this scale, we don't see much of a flux loss, at least in the quantity of the mass to flux ratio doesn't change dramatically. You can also turn this around a little bit and ask how does the magnetic field scale with the density. If you have a dramatic flux loss, the magnetic field shouldn't scale with this typical finding here with the density, with the square root of the density, but should be flatter, even and also within essentially this analysis, we don't find a dramatic change or anything. So I would say it's not a sign for a dramatic flux loss. So this is, it looks like this is not the main feature essentially to form the disk. Another feature another way to look at is the magnetic field structure. So for strong, efficient magnetic braking, what you need is essentially your disk need to be threaded by magnetic fields, which are then anchored into a medium which doesn't spin. And if you look at the magnetic field structure here, it doesn't look like essentially anything like this, what you essentially need for a strong magnetic braking effect. So the field, of course, due to the turbulence, is highly tangled. It's not it's very hard also at this point to define something like a coherent magnetic field. So a magnetic field you essentially start your simulation with. If you zoom in closer to your collapsing object, you're losing this large-scale structure, and you get a lot of field bending. And I think this is one of the main features why this magnetic braking is very inefficient in the case in a case like this, where you don't have a field anchored into a nicely anchored to a non-rotating environment. And another proposal was done by Patrick Hennebel, looking at essentially the angle of your magnetic field and the spin of your disk, and or in this case, it's actually the spin of the initial core. And you can ask yourself whether if they are misaligned, it helps quite a bit to build up a disk. But if you look at these simulations, I mean, there are cases they are highly misaligned, but there are also cases which are not. So it's fairly scattered. There is no clear trend here. It's a little bit the other way around, that it seems to be a trend, and this is something one has to probe in more detail with a better statistic. There seems to be a trend that the field line and spin might get aligned over time. So, but again, I want to note here that it is actually tough to, to define something like a large-scale magnetic field, which you then can compare with the spin axis of your disk, because you are essentially lost your nice large-scale magnetic field as shown here. So it's really, it's everything but trivial to do this comparison. Okay, that's essentially I wanted to bring out here again is I guess we kind of ran into a problem theorists did by themselves, so essentially an artificial problem by starting simulation with unrealistic initial conditions. And it seems to be fairly easy actually to form protostellar disks even in class 0 objects. So very early on, if you start with a little bit turbulence in your simulation, and this is also confirmed by a couple of other people, so with Santos Limas and also this work by Myers. Chris was talking on Wednesday about it. But of course, what is still ongoing is the main mechanism. Why do we form actually this disk in a turbulent environment? This is not fully clear, and more research has to be done on this topic. Thank you. Are there questions to this?
Yeah, I have one question. Can you go back a couple slides to the slice? Yeah, this one right here. Can you just, when I read this paper, I was really confused.
Mm-hmm.
Spiral. They don't seem to observe it be. Is this a slice?
It is a slice, so one has to be very careful here. So this is just, it's not following a field line per se. So there's the third dimension is missing. It's just a slice in this projection. It is kind of misleading, but I think it brings the point along that we are losing a large-scale magnetic, coherent magnetic field here.